Imagine two ECUs that perform the same vehicle function, but they use different microcontrollers, different peripheral layouts, and different hardware drivers. If the application code had to know every register, every driver, every memory device, and every communication controller, moving or reusing that function would become painful. AUTOSAR Classic is designed to reduce that coupling. Its layered architecture separates what the vehicle function wants to do from how the ECU hardware actually makes it happen. In the previous lesson, we separated AUTOSAR Classic from AUTOSAR Adaptive. Classic is the platform you commonly associate with deeply embedded ECUs and a microcontroller-based software stack. Now we are going to zoom inside that Classic stack. At the highest level, AUTOSAR separates the software into three major layers: application software at the top, the Runtime Environment, or RTE, in the middle, and basic software, or BSW, below it. Under the software sits the microcontroller hardware. This simple map is the foundation for almost everything we will study in the next several lessons. Start at the top. The application software contains software components, often shortened to SWCs. These components represent vehicle functionality. In our course-spanning temperature and cooling fan example, we might have a temperature sensor software component that provides a temperature value, and a fan control software component that decides whether cooling is required. The important point isn't the exact component names. The important point is that application software should focus mainly on functional behavior, not on which microcontroller register contains an ADC result, or which exact hardware driver controls an output. That is the first separation boundary. Directly below the application is the Runtime Environment, or RTE. AUTOSAR describes the RTE as the interface used by the application layer for communication between software components and for access to basic software. Think of it as the application-facing communication and integration boundary of a configured classic ECU. If one software component needs data from another, the RTE participates in realizing that connection. If an application needs a standardized service from basic software, that interaction is also exposed through the RTE, where the AUTOSAR model defines it. The RTE is not a hardware driver, and it is not simply another application component. Its job is to keep application software from being tightly coupled to the implementation details underneath. Now move below the RTE. Basic software provides the standardized infrastructure that lets the ECU operate as an automotive embedded system. This is where you encounter capabilities for communication, memory, diagnostics, operating system behavior, network management, hardware access, and many other platform functions. The key distinction is that basic software is not where you normally implement the vehicle feature itself. The application decides what the feature should do. Basic software provides the reusable infrastructure needed to make that decision executable on a real ECU. For a beginner, the most useful basic software map has three major layers: services, ECU abstraction, and the microcontroller abstraction layer, usually called MCAL. AUTOSAR also defines complex drivers as a distinct part of the basic software architecture. These names are easy to memorize and easy to misunderstand, so connect each one to the problem it solves. Services provide higher-level platform infrastructure. ECU abstraction reduces dependence on the way devices are arranged on a particular ECU. MCAL reduces dependence on the details of the microcontroller and its peripherals. For this overview, just remember complex drivers as a separate basic software area. We will examine its special role in its own lesson. The services layer is the upper part of basic software in the classic mental map. It contains infrastructure such as system services, communication-related services, memory-related services, diagnostic functions, and other standardized platform capabilities. When an application ultimately needs something like communication, persistent storage, diagnostic handling, or operating system support, the required path is provided through configured AUTOSAR infrastructure rather than every application reinventing those capabilities. Services are therefore about common ECU-level software capabilities, not direct control of a transistor or motor. Below services is the ECU abstraction layer. Its job is to hide details of the ECU hardware arrangement from the layers above. An external device might be connected through one microcontroller peripheral on one ECU design and through a different arrangement on another. ECU abstraction provides standardized access patterns so upper software doesn't need to understand every board-level detail. AUTOSAR groups areas such as I/O hardware abstraction, communication hardware abstraction, memory hardware abstraction, and onboard device abstraction in this region. The exact modules present depend on the ECU configuration, but the architectural purpose is stable. Isolate upper software from ECU-specific hardware layout. Closest to the microcontroller is MCAL, the microcontroller abstraction layer. This is where standardized drivers access microcontroller peripherals and hardware resources. Depending on the ECU, that can include I/O drivers, communication drivers, memory drivers, and microcontroller drivers. ADC, digital I/O, PWM, and CAN driver concepts live at this hardware-facing end of the stack when they are part of the configured system. MCAL does not make the hardware irrelevant. It creates a standardized software boundary around hardware-specific access, so the upper basic software can be less dependent on a particular microcontroller family. Now, look at the whole stack through one concrete path. Suppose a temperature sensor produces an electrical signal that the ECU measures. At the bottom, the microcontroller peripheral receives that signal. An appropriate MCAL driver accesses the peripheral. ECU abstraction can hide details of how that sensor is connected on this ECU. Through the configured AUTOSAR interfaces and the RTE, the temperature sensor software component can receive a usable value without reading a hardware register directly. The fan control software component can then decide whether cooling is needed. For the output direction, the request travels back through the appropriate configured interfaces and basic software towards the microcontroller output. The last motor driving action is different. The low-power microcontroller control signal then drives suitable external power electronics, and those power electronics supply the fan motor. This is why the layered architecture matters. Without these boundaries, application code becomes entangled with microcontroller details, board layout, communication hardware, memory technology, and project-specific integration choices. A hardware change can then force changes far above the hardware. AUTOSAR doesn't magically eliminate all project work, but the separation supports hardware-independent application development, standardized basic software, software integration from different sources, and reuse across ECU variants when the interfaces and configuration allow it. If an interviewer asks you to sketch AUTOSAR Classic architecture, start with the simplest correct answer: application software at the top, RTE underneath, basic software below that, and the microcontroller hardware at the bottom. Then expand basic software into services, ECU abstraction, and MCAL, with complex drivers shown as a distinct basic software area. Explain the responsibility of each boundary instead of only reciting the names. If you want the architecture to become something you can reason about rather than memorize, subscribe and continue through the layer-by-layer walkthroughs. We have now built the complete map. The next question is what actually belongs inside the application software layer, how software components represent vehicle functions, and what should stay out of application code. That's where the next lesson starts.